All right, so let's do some more volume examples, and in particular, let's concentrate on how we make decisions on are we going to integrate with respect to x or are we going to integrate with respect to y, which then tells us are we going to use the washer method or are we going to use the shell method. All right, so let's look at this one. We have the volume of the solid obtained by rotating this region around a new line. Instead of one of the axes, we're going to do this y equals -2. Now, in this problem, they give us a function of y, right? They give us x in terms of y. If we have a function of y, that indicates right away that we probably want to integrate with respect to y. Don't have to. If we can switch it around, we can. But in general, if we're given functions of y, if we're given things in terms of y, we're probably going to integrate with respect to y. If we're going to integrate with respect to y, that means we're going to slice our region perpendicularly to the to the y-axis in this case, right? If we're going to integrate with respect to y, that means we're chopping up the y-axis. It means we're slicing this way, perpendicular to the y-axis. That means if we were to imagine a rectangle in our region here, those rectangles will be parallel to our axis of rotation. Rectangles that are parallel to the axis of rotation means that we create shells when we rotate. For the shell method, then again, remember we need a radius and a height of the shell. All right, so let's think about the radius of the shell. Go back up here. Well, our shell is going to be at some particular y value, and it has to rotate down to y, or around y equals -2. So our radius will be the distance from that rectangle to the axis of rotation. It's at a height of y, and the rotation line is at a height of -2. So the radius of the shell will be y minus a -2, or y plus 2. Again, going back to the picture, the shell gets its height from the rectangle that you would imagine in here. The rectangle goes from 2 down to y squared and plus 1. So subtract those two values, you get 1 minus y squared for the height of the shell. Last thing we notice, the two curves, x equals y squared plus 1 and x equals 2, intersect when y is plus or minus 1. You can see that in the graph, but of course the main way you would find this would be to set them equal to each other and solve. Done that in algebra class a number of times. So now we plug it into our formula for finding volumes with the shell method. 2 pi integral from -1 to 1, because that's what our y's run through. Radius is y plus 2. Height is 1 minus y squared. Distribute. Anti-differentiate. Plug in the endpoints and simplify. Let's do another one. All right, excuse me, let's do this one again, but let's also notice that we could have used the washer method. Washer method, to create washers, I would have done slices that are perpendicular to the axis of rotation, right? This way. Which means we would have to integrate with respect to x, which means everything has to then be in terms of x, which means I need to solve for these top and bottom bounding curves in terms of x. So we took the function x equals y squared plus 1 and solved for y. That means we would get y equals a positive root x minus 1, that's the top part of this parabola, and a y equals a negative root x minus 1. That'd be the bottom of that parabola. All right, so remember that your radius for the washer has to be from axis of rotation to that farthest away bounding curve. So it would be square root of x minus 1 plus 2, because you'd be doing a minus and minus 2. Likewise, then you would have that should be negative of x minus 1, negative of square root of x minus 1 plus 2. So these signs are full. Good news is it won't matter because I have the negative of what I should have. The bottom bounding curve here is negative root x minus 1, and we're going to subtract -2. So it should be the negative of square root of x minus 1 plus 2 here. But again, remember how we do the volumes of washers. It won't make it, the fact that I've got the wrong signs here on both terms won't make any difference, because when you square it, it'll come out in the wash. All right. Now again, we have to remember if we're going to integrate with respect to x, everything has to be in terms of x. So we have to change our limits of integration to x's. Well, we can see from the picture that our x's go from 1 to 2 in this case. Certainly our right endpoint is 2, and you can figure out this point pretty easily because that's the vertex of the parabola is 1, 0 in this case. All right, so the volume. Remember for washers we do pi times the bigger radius squared minus the smaller radius squared, and this is why I said that it didn't matter that I had the signs wrong here. If I had a negative here and a positive here, that's the exact opposite that we're squaring. So the squaring would just kill the fact that I made a sign error there. So we've got big radius squared minus little radius squared. Distribute everything out. Simplify, you'll just get square root of x minus 1, and you can pop an 8 out in front afterward. Antiderivative here, we had 2/3 times x minus 1 to the 3/2. This is where the 16 pi over 3 comes from. It's 8 pi times 2/3. Plug in your endpoints and get 16 pi over 3. Let's do another one. We want to revolve the region bounded by y equals 4x minus x squared and y equals 3 about the line x equals -1. Again, we're given function of x, so we're going to choose to integrate with respect to x. We could do this with respect to y, but if I did that, I'd have to solve this for x, so I'd have to use the quadratic formula to solve for y, x in terms of y. That doesn't sound like fun to me. So integrate with respect to x. That means we're going to slice perpendicular to the x-axis. That creates rectangles that are parallel now to their axis of rotation. So it's a shell method. Shell method requires a radius and a height. The shell goes from x to -1, so x minus a -1 gives you x plus 1. The height of the shell would be the height of the rectangle imagined in here, 4x minus x squared minus a -3. Or, excuse me, -3, not minus a -3. Again, you can check for when these two curves intersect, be it 1 and 3. We can see it on the graph or just set them equal to each other. Volume of the solid then is going to be 2 pi, integral from 1 to 3, radius times height. Doing the integral, we'll distribute everything out. Anti-differentiate, plug in your endpoints and simplify and get 8 pi. Right. Let's look at this one. Similar problem except I changed the bottom bounding curve to y equals x instead of y equals 3. I'm going to rotate this one about x equals 5, so that would be over here. Again, I want to integrate this with respect to the x-axis really badly. One, I already mentioned in the previous one. Solving for this for x is going to not be a fun thing to do, right? I have to use a quadratic formula to do that. Second, notice that if we slice perpendicular to the y-axis, I have to use two integrals because I have my right bounding curve changes. I'd rather not have to do two integrals. I'd rather not do two integrals unless I absolutely had to. I'd rather set it up and do it with one integral instead of two. So that's another reason why I do not want to integrate this with respect to y-axis. Notice I haven't said anything about I want to use method A or method B. I said I want to integrate with respect to which x or y, and then decide what, or excuse me, and then use that decision to tell me what method to use. All right. So I'm choosing to slice it vertically, to slice it perpendicular to the x-axis. As soon as I do that, and notice my axis of rotation is parallel, I get shells. Okay? That's how I get the method. Not, I'm going to apply the shell method to this problem. It's I have this problem, I'm going to choose my variable to integrate with respect to, and then I see what method I have to use. Okay? So I'm not picking the method first. I'm picking the axis of integration first. All right. So like before, radius is going to be from axis of rotation to the x value. Notice in this case I do 5 minus x as opposed to x minus 5 because the 5 is bigger than anything over here that's in the region for x values. The height of the shell is just the difference of the two functions, just that height of the rectangle that would be in your region. Again, set the two curves equal to each other to get the bounds on your integral. Use your volume of a shell for the shell method formula, 2 pi radius height dx over your interval. And then again, just like we've done before, do your multiply everything out and do an antiderivative and plug in your endpoints, and you'll get 63 pi over 2. All right, one more example. We're going to find the volume of the solid generated by rotating the region y equals 2x over 1 plus x cubed and y equals x about the line y equals -1. All we're going to do in this one is we're just going to set the integral up. We're not actually going to evaluate the integral. It's possible we absolutely can evaluate this integral. It just requires a technique of integration that we haven't talked about yet. So we're going to save that technique of integration for later, and we're just going to set the integral up. All right. Again, I want to integrate this thing with respect to x really badly, okay? Because this is function of x. This is function of, well, x, the way it's written. So, but also notice here that again, up here, it's kind of hard to see, but notice that this thing goes up and back down again. I would have a different right bounding curve here than I would here. So you'd have to use two integrals again, just like the previous problem. So the shape of the region and the format of the function is telling us that we want to integrate this with respect to x, not y. Okay? You could solve this for x. It requires something referred to as Cardano's formula. Again, you probably have never seen that before. If you have, congratulations. Not a lot of people at this stage would have seen it. Okay? But I don't want to. It makes it not a nice thing to try to deal with. I can do this in another way. I can just choose to integrate this with respect to x anyway. Right, but I've got two regions that says that we should integrate this with respect to x and not y. All right, so now I've got, if I'm integrating with respect to x, my slices go this way, perpendicular to the x-axis. And they're also perpendicular to the axis of rotation. That tells us that we're using washers. Washers again, big radius and a small radius that we need. Big radius, the top curve is this 2x over 1 plus x cubed. The bottom curve is x. So our larger radius will be 2x over 1 plus x cubed minus a minus 1. Our smaller radius will be the x minus a minus 1. Again, we can figure out the points of intersection either from the graph or just set them equal to each other and solve. In this case, you get x equals 0 or x equals 1. Now we're using the washer method to evaluate this volume. So it's pi times big radius squared minus little radius squared, and then integrate it from 0 to 1. Again, we're going to leave it here as an integral because we don't want to take the time to learn an entire new method of integration just so that we could finish off this problem. I mean, you could just finish off this problem by putting it in a calculator and getting an answer. So, all right. So that gives you a few more examples of using the different methods that we've talked about to find volumes of solids of revolution.